weather is so nice. A cup of hot chocolate could make my day. Wow! Is it chocolate powder? I must be blessed because I'm smart. But I don't have hot water here. What should I do about it? Heating water with solar energy? Aha! Sunlight can heat water. Got it! Aha! The weather is so good. The water will be heated up and I can make a drink soon. I even save money for electricity and gas. Life's so easy. Ha ha! Stay here and I will be back soon. Oh my goodness! Why is half of the water gone? Shouldn't the sun have heated it for me? How come?
Water cannot be heated in this way. It is not so simple to heat water with sunlight. Traditional heaters rely on the energy generated from fossil fuels. Combustion of fossil fuels causes the emissions of greenhouse gases and makes the earth hotter. Your environmental awareness is appreciated. Let me show you a solar water heating system. A solar water heating system consists of solar collectors, storage tanks, and pipes. Solar collectors are installed in places well illuminated by sunlight, such as rooftops. Some collectors consist of small pipes allowing water at room temperature to flow through. When the collectors are exposed to sunlight, solar energy is converted into heat and warms the water inside.
How come half of the water disappeared?
Is that my chocolate powder?
Ugh. Hello, Dr. Tong. I meant to prepare it for you, but I don't have hot water, so I tried to heat it with sunlight, and now I've only got half of it left.
Of course it doesn't work. Water will evaporate. I was going to talk about the 3 heat transfer processes. Do you know about them?
I have no idea. I just heat water on a stove.
When you boil the water, the fire heats up the pot, which then transfers the heat to the water. Heat must be transferred by some means. There are 3 types of heat transfer processes. The first one is conduction. Conduction refers to heat transfer from a hotter place to a cooler place through the vibration and collision of particles. The second one is convection. Convection only occurs in liquids and gases because they are free to flow. As they flow, heat is transferred from one place to another. The third one is radiation. Heat is transferred through electromagnetic waves, such as visible light and infrared radiation. All hot objects emit infrared radiation. EM waves can travel through a vacuum. They don't require a medium. They can travel a long distance. That is why light and heat from the sun can reach the Earth through a vacuum.
I think I understand.
But you look confused. I have 3 experiments to show you. Let's do the experiments together and you will understand it.
All right.
Let's go.
Wow, Dr. Tong, what are these black things?
Guess what they're made of?
Is it aluminium?
No, it's copper. It is quite heavy. What about this?
It seems like iron.
It is stainless steel. And this?
It's so light. Is it plastic?
You've got it right, finally. This experiment aims to do a test by heating these 3 containers with sunlight to find how efficiently the materials conduct heat. This is called thermal conductivity. The test needs to be fair. Since we are now testing the thermal conductivities of different materials, all the other factors must be kept constant for all the 3 containers. For example, the sizes of the containers are the same. All of them are painted in black. The thickness is also the same. We will add water to the containers. The volume and initial temperature of the water are the same. How do we measure the temperature of water? We use these thermometers. They are connected to a tablet with Bluetooth connections, allowing us to see real-time data. We will put them under the sunlight and observe how their temperatures change.
I'm more than ready. Shall we bring them outdoors now?
Sure.
Why do we cover them? Why not just expose them directly?
Remember that the test needs to be fair. While bringing them outdoors, I want to avoid one container from receiving more sunlight than the others. That would be unfair. That is why we cover them before the experiment begins, so that they don't receive any sunlight. Once the experiment begins, they are uncovered at the same instant, thus the test is fair.
How long will it take?
It will take 20 minutes.
We can leave once they're uncovered.
Okay. Let's go.
It's been 20 minutes. What is the result?
Make a guess. Which one is the hottest?
Is it copper?
You're right. Copper has the highest thermal conductivity. That is why its temperature is the highest. The water inside is 51 degrees Celsius. For stainless steel, the water inside is 49 degrees Celsius. For plastic, the water inside is only 48 degrees Celsius.
It seems that copper has a higher thermal conductivity.
Yes, metals usually have higher thermal conductivity than non-metals. The thermal conductivity of copper is quite high among metals.
Apart from materials, are there any other factors which may cause errors in the experiment?
This experiment should be done carefully. In the beginning, the heating of water is faster. As time goes by, the water gets hotter. It starts to lose heat through the containers. Therefore, some preventive measures are needed. We put the containers on top of the foam mats, which insulate the containers and the bench. This reduces the heat transfer by conduction.
Oh, that's the purpose of the foam mats.
There is another problem. During the heating process, the containers also absorb some heat. But their heat capacities are different. One may absorb more heat, the others may absorb less heat. This also affects the result, but this problem is inevitable. This experiment can be related to the principle used in solar water heating systems. There are small pipes inside the systems. Water flows inside the pipes. It absorbs heat from sunlight. As those pipes are made of copper, heat absorption is more effective as copper is a good conductor.
Besides materials, are there any other factors affecting heat transfer?
Yes, there are. We will do another experiment to discover this factor.
Shall we go back now?
Okay.
Dr. Tong, we have finished the experiment about conduction. What is the next experiment?
This one is about radiation.
Radiation? Is it about colours?
Exactly, it is about colors. This time we use 3 bottles made of the same material. They are all made of aluminium but painted in different colors. By exposing them to direct sunlight, we will observe how fast the water gets heated up inside and test their ability to absorb solar radiation.
It's similar to the last experiment, but we use different colours rather than different materials.
You're right, a fair test. Let me emphasize the importance of a fair test again. We are now studying the effect of colors. Apart from the colors of the containers, all other factors have to be kept the same. The containers are made of the same material, which is aluminium. Their sizes are the same. The volume and initial temperature of the water inside are the same. This ensures a fair test.
Now I see what to do. Let me add water first. I got it this time. You want to isolate the containers from sunlight. That's why you cover them in the box.
Exactly.
How long does this experiment take?
Around half an hour. Once the containers are placed, we will leave them alone.
Okay.
Ready? 1, 2, 3. Let's go.
Dr. Tong, during summer we feel hotter when we dress in black. I think the black container should have the highest temperature.
Yes, you're right. The water in the black container is the hottest. The water in the white one is cooler. It is 7 degrees Celsius lower.
Why is black colour so effective in heat absorption?
Think about why an object appears black. It is because all the visible light is absorbed. Sunlight is white light, which contains light of different colors. The black surface absorbs all the light and thus it looks black in color. Why does a white object appear white? When exposed to sunlight, the object reflects all the light. The reflected light contains all the colors and thus appears white. Since a black surface absorbs light more effectively, it heats up faster. Inside solar water heating systems, the inner copper pipes where the water flows are painted in black. The absorption of sunlight is more effective.
Copper is good at conduction, black colour is good for absorption. The water can be made very hot.
I feel hot too.
Let's go back.
Sure.
Let's go. We're done with the experiments. It is time for a cup of hot chocolate.
Ah, not yet. We have just finished radiation heating, but we have not done radiation cooling.
What shall we do then?
We use these 3 bottles again. The colors are different. We will compare objects of different colors. Under room temperature, when hot water is filled in, we will observe the cooling effectiveness.
So we need hot water.
Yes, I have hot water prepared already. We will pour hot water into these 3 containers. Bear in mind a fair test. The same amount of water should be poured in. The initial temperature must also be the same so that the test is fair.
For the sake of pursuing science, let me.
Hey, safety first! I have some heat-proof gloves here, which can withstand temperatures as high as 200 degrees Celsius.
Okay, fantastic gloves. Let me do it. We're all set. Let's have a cup of hot chocolate, shall we?
Sure, let's come back in an hour.
Dr. Tong, it's been an hour and we have finished our drink. What is the result?
It is stored in the tablet. Guess which container cools down faster?
We have the black one absorbing heat faster. I think the black one also cools down faster.
You've got it partially right. Well, the black one cools down a bit faster. However, the white and the black ones only differ by 1 degree Celsius even after an hour.
That's so similar.
Yes, it may be due to experimental error. We are uncertain whether the black one really cools down faster. When we put them under sunlight to test heat absorption, sunlight contains mostly visible light. Black color absorbs visible light most effectively. That is why the water in the black bottle heats up faster. But now we test their ability on cooling. While cooling, the containers do not emit visible light. What do they emit? They emit infrared radiation. They cool down by emitting infrared radiation. But the emission of infrared radiation is not quite dependent on the surface color. As a result, the black and white containers show similar results.
I see. Even if we dress in black indoors during summer, we won't cool down faster.
Yes, that is a common misunderstanding. While doing this experiment, we should pay attention to some details. Did you notice the foam mats? We want to test the cooling effect, which is due to radiation. As the containers are placed on the bench, some heat is transferred to the bench by conduction. We want to reduce such effects. So we use the foam mats to isolate the containers from the bench. Moreover, the containers heat up the surrounding air, and heat is taken away by the convection of air. This effect is inevitable. What we want to show in this experiment is that the rates of radiation cooling are similar among different surface colors.
There are so many factors to consider in the experiment.
Yes, it's not that simple.
Dr. Tong, we have tested different materials and different colours as well. What shall we do next?
We will see the effect of heat insulation by a layer of air.
A layer of air? Like a waffle?
Something similar, but it is not with cream inside. It is air inside. This test tube is single-layered. This is a test tube placed within another, so that there is a layer of air in between. We will test the effect of this air layer on heat insulation. We will add hot water into the test tubes. Then, we use the wireless thermometers to observe how the temperature changes. We will wait for 25 minutes and see how the temperature changes.
We use hot water again. I have the gloves prepared. Dr. Tong, it's been 25 minutes. Is there any significant difference?
The data are here. The water cooled down from 60 degrees Celsius. In 25 minutes, one dropped to 37 degrees Celsius, the other dropped to 32 degrees Celsius. Can you tell which one is which?
This one's 37 degrees Celsius.
You're right.
Oh, I got it right.
Since this test tube is double layered, air is trapped inside. The cooling is thus slower, and the temperature is higher. Let me explain how the air layer makes cooling slower. If there is only one single test tube, it heats up the surrounding air. The airflow carries heat away. Now, we put one test tube within another and trap the air in between using plasticine so that it cannot go away. Heat loss is thus reduced. Also, the thermal conductivity of air is very low. It's like covering yourself with a quilt. The air inside keeps you warm. With both factors together, the heat transfer is much reduced. Therefore, the temperature of this test tube is 5 degrees Celsius higher.
I got it. The principle behind is like the vacuum flasks we use. The layer of vacuum helps reduce heat loss.
That's right, you're smart.
Dr. Tong, we've done many experiments with sunlight, but how do we know the amount of solar energy that actually goes to the water? Or does it just go to our heads?
I know, the weather is hot. But you have asked a good question. The purpose of the next experiment is to find out how much energy from sunlight actually goes to heating water.
Do we know the amount of energy gained from sunlight?
It is simple. We have a solarimeter. What does it measure? It measures the amount of solar energy received by a surface of 1 meter squared each second. After getting the data on solar radiation, we multiply it with the area of the container that is exposed to sunlight, and then multiply the duration of heating. The product of the three numbers gives the total amount of solar energy reaching the container. Besides the solar energy reaching the container, we also need to know the heat absorbed by the water. The way is to measure the rise in the water temperature within that period. We need to know that for 1 kilogram of water to be warmed by 1 degree Celsius, the amount of energy needed is 4,200 joules. This is called the specific heat capacity of water. The mass of water is multiplied by the change in temperature and the specific heat capacity of water. The product gives the heat gained by the water. Dividing the heat gained by the water with the solar energy reaching the container, we can calculate the percentage of solar energy that goes into the water. This is the efficiency of heating.
I have learnt a lot, but it's too sunny. Shall we start doing the experiment?
We will wait for 20 minutes. Let's go to the shaded area.
Sure, that way. Dr. Tong, it's been 20 minutes. What is the result?
After calculation, I found that the efficiency of water heating is about 64.3% within 20 minutes. That means about 60% of the solar energy is used to heat up the water. That is the efficiency. But there were some technical issues in the experiment. As the water got heated, it became hotter and started losing heat to the surroundings. The longer time it is heated, the lower the efficiency. In the beginning, the temperature rose rapidly because of effective absorption. When the water is heated to a certain level, the temperature rose slower and leveled off.
I see. The rate of temperature rise gradually slowed down.
In practice, the solar water heating systems are different from our experiment. In the experiment, the water could not flow. However, the water is circulating inside the pipes of the solar water heater. The water enters the pipes and gets heated up by sunlight. Then it leaves the pipes and is stored in a tank somewhere. New water will flow into the pipes and gets heated up again. This efficiency would be the highest. Water can absorb the maximum amount of sunlight.
That seems to be very efficient and can save a lot of energy.
That's right.
From the experiments, we have learnt the science of heat. The knowledge is very useful. Let me show you the solar water heating system installed in the headquarters of EMSD. The system adopts evacuated tube solar collectors. It applies the science principles we've just learned to increase the efficiency of heating. The glass tubes inside are double layered, with a vacuum in between to keep warm. The inner glass tube is painted in black. It enhances the absorption and conversion of sunlight into heat. The pipes in which water flows are made of copper. It makes the conduction of heat more effective to heat up the water inside. The solar water heating system mainly supplies hot water to the bathrooms, in the workshops, and the canteen in the headquarters. According to the data in 2020, 7% of total energy consumption in Hong Kong is used for producing hot water. The energy is generated mainly from the combustion of fossil fuels. It leads to a large amount of carbon emission. The benefit of solar water heating system is to heat up water by sunlight directly. Fossil fuels are not involved in the process. No carbon dioxide is emitted. The users can save money while contributing to environmental protection.